Hello everyone, welcome to today's video. In today's video, we are going to discuss about one of the most important predictive modeling technique, that is multiple linear regression based on HR analytics. I'll be showing you all how to implement HR analytics, how to implement multiple linear regression using HR analytics on R. So let's proceed. Now the agenda today is, first I'm going to discuss with you all the project we are going to work upon for multiple linear regression on HR analytics, the primary goals, the concept of multiple linear regression, and how to practically implement multiple linear regression in R. So first let's understand our project. Our main focus will be, we are going to analyze over here employee satisfaction, which are based on certain predictive factors. Now the employee satisfaction over here will be a dependent variable, and you have multiple independent variables which are influencing our dependent variable. Now the independent variables are factors which are rated from 1 to 10, and the employee satisfaction score are also noted, and using the independent variables we will be predicting the value of our dependent variable. Now, how are we going to approach this particular project? Our main motive will be first that we have to first identify or recognize the significant independent variables that are creating impact on our dependent variable. And then we are going to develop the predictive model to forecast the value of satisfaction. So, regression analysis is all about investigating the relationship between a dependent variable and independent variables. Now we call it as multiple linear regression analysis because we are going to use multiple independent variables to predict the value of our dependent variable. Now there are certain steps which you need to follow to do multiple linear regression. The first step is we have to explore our data and we have to pre-process our data, that is we have to do data manipulation part, that is to prepare our data so that it is ready for our analysis. Next we have to select the set of independent variables which are creating significant impact on our model or which are relevant for our model. Then we are going to build the model, that is we will build the multiple linear regression model based on our data. Then we'll do the prediction, and the last is we have to check the goodness of fit, that how good is our model fit. Now the basic results which will help us to draw interpretation from our model is first the coefficients of our independent variables, seeing whose value we can understand how the independent variables are related to the dependent variable. We can check the magnitude and the direction. Direction we can check using the sign, and magnitude, using the magnitude we can check the amount of association between the dependent variables and the independent variables. And the next is R square, which shows us how well is our model fit or how good is our model fit. Then we are going to build the predictive model technique to predict the value of our satisfaction score or employee satisfaction based on the different predictive factors. So after identifying the different predictive factors which are going to be creating a significant impact on our model, we are going to build the linear regression model, and accordingly we can guide the HR or the company can guide the HR or can take relevant strategies. So our main motive will be analyzing the relationship between our employee satisfaction and various other factors influencing employee satisfaction to forecast the value of the satisfaction or to get the satisfaction score for different employees. So now let's discuss the primary goal. So the primary goal of our project is analyzing employee satisfaction and predictive factors. So now let's discuss about the objective of our project. The satisfaction score of different employees of a company is affected by number of variables. The HR of the company wants to analyze the relationship of the dependent variable with the different independent variables. The employee satisfaction needs to be predicted using the number of factors. All the factors are are weighted from 1 to 10. So using the different factors which are weighted from 1 to 10, we are going to estimate or predict the value of our employee satisfaction, which is our dependent variable. And the rest of the factors are our independent variables. So first objective is to understand the concept of multiple linear regression, and then our main purpose is to build the multiple linear regression model to predict the value of our dependent variable based on different independent variables. Now the different key terminologies that we are going to come across to do this particular project is, first, the variable that we want to predict, that is our response variable. We call it also as a dependent variable. The different factors which are going to influence the response variable or the dependent variable are the predictors or features or independent variables. And then we are going to extend from simple linear regression model to multiple linear regression model, because we are going to use multiple predictors or multiple independent variables to predict the value of our dependent variable. So therefore we call it as multiple linear regression model. Now what are the different situations where you can use multiple linear regression? You can use or you can apply the technique of multiple linear regression when you have one dependent variable and multiple independent variables, where the dependent and the independent variables are linearly related to each other, or we can say there is a presumed linear relationship between the dependent and the independent variables. Now let's come to the standard form of multiple linear regression model. The standard form of multiple linear regression model looks like y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot till beta k xk plus ei, where beta naught is your intercept, x1, x2, x3, dot xk, these are the values of your independent variable, beta 1, beta 2, beta 3, dot beta k, these are the coefficients of the independent variables, and ei, that is E is the error term and I stands for the ith observation. E is the error term or the residual terms. Now let's discuss about the different assumptions of multiple linear regression model. The first assumption of multiple linear regression model is the relationship between the variables should be linear. Second, observations should be independent of each other, that is they should not get influenced by each other. Third, the assumption of homoscedasticity, that is the residuals should have constant variance, that is there should be consistency in the residual terms or error terms. Error terms should be constant, it should not change. There should not be too much inconsistency in the residual terms. Residuals or the error terms should follow a normal distribution. And the most important is the independent variables should not be correlated among each other. There should be minimum level of multicollinearity among the independent variables. Now, the different steps that we are going to follow to build our linear regression model is, first we will collect the data and prepare our data, that is we have to manipulate our data, pre-process our data to prepare a data set which is suitable for linear regression. Then the relevant or the significant independent variables should be chosen which are relevant for our model or which is going to create a significant impact on our dependent variable. Then we are going to fit the model or build the model using the significant or the chosen variables, and then we are going to do the model evaluation, that is which includes the prediction of our dependent variable, and then check that how well is our prediction done or how good is our model fit. So assessing the goodness of fit of our model with the help of the different significant independent variables. Now the different results that will create a significant impact or that holds some importance for our model is, first is the coefficients. Coefficients, that is beta 1, beta 2, beta 3, or beta k, these are the coefficients of our independent variable. This represents the change in our dependent variable for a unit change of our independent variable, that is the change that will happen to our dependent variable for a unit change in the respective independent variable holding other variables constant represents the coefficients of the independent variables. R square is the explained variation, R square is equals to the ratio of explained variation by total variation. So R square measures the amount of explained variation of our model, which ranges from 0 to 1. Okay. There is a concept of root mean square error, which measures the model accuracy, and there is a concept of adjusted R square, which is R square adjusted to the degrees of freedom. Now let me explain you all the concept of R square and adjusted R square. As I told you, R square is the ratio of explained variation by total variation. Now this explained variation is the amount of the dependent variable that is going to be explained by the independent variables. That is your explained variation. Total variation is explained variation plus unexplained variation. Unexplained variation is the amount of the error terms or the amount of the dependent variable that remains unexplained. So technically, if your R square is equals to the ratio of explained variation by total variation, then if the number of independent variables are increased in the model, automatically your explained variation will increase, because independent variables are only the explained variation part of the model. So if your independent variables increases, then explained variation increasing, then you can conclude that my R square explained variation is increasing in my model. The R square value is going to increase. That shows that the model is a very good fit. But here there is a concept which you need to take into account, or which you need to consider. When we are increasing the number of independent variables in our model, the individual significance of the independent variables, that is how much individually each of the independent variables are creating impact on our dependent variable, are not tested or are not considered. Therefore, the concept of adjusted R square plays a very important role, that is R square adjusted to the degrees of freedom. Adjusted R square considers only those independent variables which creates significant, or individually it creates significant impact on our dependent variable. So, in order to sum up, we can say that adjusted R square value, if it is high, we can say the model is a very good fit, because that only considers the significant independent variables. Because if you increase the number of independent variables, automatically R square value is going to increase without considering the individual significance of the independent variables on the dependent variable. So, adjusted R square plays a very important role in order to understand the significance, or how significant impact the independent variables are creating impact on dependent variables. So, adjusted R square is R square adjusted to the degrees of freedom. Higher the value is your adjusted R square, better is your model, and we will always see that adjusted R square value is always less than the R square value, because R square considers all the independent variables, whereas adjusted R square considers only the significant independent variables which are creating individual impact on the dependent variables. Now, the different form of data visualization plots that are done in multiple linear regression model are like scatter plots, residual plots, plots between predicted value and the actual value, that is the observed value and predicted value. These are the different types of plots that are done in multiple linear regression model. Now let's practically understand how to implement multiple linear regression using HR analytics on R. So our first step will be, we are going to import the data set into R. So the data set that we are going to work upon is an HR linear data set. So first let me explain you all the code. I have given an object name as HR. Then read.csv. This is the assignment operator. This operator stands for assignment operator. Instead of this arrow, you can also use equal to sign. Equal to sign also stands for assignment operator. Read.csv function. Then within bracket, within quotations, you are giving the path where your data set is located, and at last you are giving the name of the data set. Close the quotations, comma, header equals to true. That is, you want the column headings. So in this way, let's import the data set, view it. So this is my HR data set. So see, This is employee satisfaction. This is employee ID. Employee satisfaction is my dependent variable, and from salary till promotions, these are all my independent variables that is going to be used to predict the value of the dependent variable. The next thing that we are going to do is we are going to generate random numbers using the function set.seed25. This random numbers is going to be generated because we are going to divide the data into two parts. That is, one portion of the data will be training and the another portion will be testing. We will be building the model on the training part, and then we will be applying the results of the training model on the testing data. Now you can change the seed value as per your choice. I have given it as 25. You need to understand another thing, because you have generated random numbers. When we divide the data into two parts in a particular ratio, the division will never be exact because we have generated random numbers, so the division will be approx, not exact. So see, here we are dividing the data into two parts, training and testing. Size equal to n row HR, this is my name of the data set. So number of rows of HR are taken. Replace equals to true. Replace equals to true means without replacement. And here we are dividing the data into two parts where 70% is training and 30% is testing. So we are dividing in 70s to 30 ratio. This ratio you can change, it's up to you. So now 70% is going to be training, 70% of the data will be replaced by training and 30% will be replaced by testing. This division will not be exact because we have generated random numbers. So now see, 70% of the values are replaced by training and 30% of the values are replaced by testing. Now let's check the class of Ranuni. I have divided the data into two parts and I have stored it in the Ranuni object. Here the values are 70% of the values are replaced by training and 30% of the values are replaced by testing, and it is stored in a Ranuni object. Now I am checking the class of it. Class is used to check the data type of an object. So it's a character data type. Now whatever values inside Ranuni are training, corresponding to those values, whatever observations are there in my HR dataset, those will go to training data. So this I am doing to do the actual division, that is to get back to my original observations. So all the values corresponding to training present in Ranuni, that are present in the HR dataset, all the observations corresponding to training values of the Ranuni in HR dataset are going to go to training data. So if you check the number of rows of training data, it's 152. Similarly, all the values inside Ranuni which has testing corresponding to that, whatever observations are there in the HR dataset are going to go to testing data. Check the end row of testing data. So training data had 152 observations, so remaining will go to testing data, that is 48 observations. Now what I am going to do, now I will be taking the names of the independent variables. So the column names are the names of the independent variables. So my independent variables are starting from 3 to 15. So see, from the third column, that is from salary, till the 15th column, that is promotions, are our independent variables or the predictive factors. So I am taking the column names from 3 to 15 from the HR dataset, and I am storing it in an object called int variables, which stands for independent variables. So these are the list of the independent variables or the predictive factors of our model. So these independent variables will be used to predict the value of the dependent variable. Now I am going to form the right hand side of the model. Right hand side of the model is what? It has a list of independent variables which are separated by plus sign. So I am going to join all the independent variables using the paste function, and I am going to separate them by plus sign. That's why I have used the collapse keyword, and I am storing it in RHS of model, that is right hand side of the model. This is my object name. So see, the right hand side of the model, it is created, consists of all the independent variables: salary, working hours, technical support, complaint resolution, work culture, working hours, bonus, incentives, appraisal, number of leaves, medical facilities, transport allowance, promotions. These are other different independent variables. Now let's check the class. of RHS of model. The class is character. Now, in order to form the whole model equation, I need to bring the left hand side of the model which has the dependent variable, and I need to paste that with the right hand side. So I am pasting the left hand side of the model, which is employee satisfaction, with the right hand side of the model and storing in an object called model. So the whole model equation is formed. Here you note that in normal model equations we use equal to signs, but over here we have used this relational operator because equal to sign in R is considered as assignment operator. So instead of equal to, we use this relational operator. This is called relational operator. So now let's check the class of model, its character. Now I am going to convert this character data type into a formula data type. Using as.formula, formula, I am going to apply the as.formula formula function on model, and I will store it in an object called FRM. So let's check the class of FRM. So now it's a formula. Now on this formula, using the formula, I am going to build the linear model using the LM function, and I will fit the training data in my linear model and will store the entire model in an object called training model. You can change the object names as per your choice. So this is my training model. See, in the training model, the coefficients of all the independent variables are given. The intercept values are also given. Salary coefficient is given, working hours, technical support, content resolution, work culture, all the coefficients are given. Now let's check the class of training model. So now it's a linear model, and then let's check the summary. You see, in the summary of the model, you have the significance of all the variables. Now the p-values, the variables whose p-values are between 0 to 0.001, they are marked as triple stars. Variables whose p-values are between 0.001 and 0.01 is marked as double stars. Single star is where p-values is lying between 0.01 and 0.05. Dot is between 0.05 and 0.1, and space is between 0.1 and 1. These are symbolics, annotations. Now here the most important measure which we will use for our interpretation is, here we can see the multiple R square value and adjusted R square value. As I already explained to you that adjusted R square value is always less than multiple R square value, because adjusted R square value only considers the significant independent variables that are creating impact on the model. So that is 79.79 and 81.53 is a multiple R square value. So here you can see your total explained variation is 81.53%. That is 81.53% of our dependent variable can be explained, and when that is adjusted to the degrees of freedom, 79.79% of the dependent variable is explained. Now we can do certain improvement in our model by doing feature selection. So we will be doing feature selection in order to improvise our model. So we will be applying step function to do stepwise selection. Direction equals to both means we are going to do forward selection and backward selection simultaneously in order to do stepwise selection to get only the significant variables that are important for our model. So let's do this stepwise selection. So see, this is the result of my stepwise selection. Stepwise selection is done. You will see that in every step, beginning of every step, the AIC values are mentioned. AIC is another important measure that is used for our interpretation. It's a very important measure. AIC stands for Akaike Information Criteria. Akaike Information Criteria measures the amount of unexplained variation of our model. So lesser is the value of our AIC. So lesser is our AIC value, lesser is the unexplained variation, better is our model. In our case, you see in stepwise selection, the model is arranged in descending order of AIC value. So as you go down, the AIC value is reducing, it's decreasing. And you see the last step, when we reach the last step, this is our last step, which is giving the least value of AIC. So this is the least value of AIC that can be achieved for our model. And these are our salary, working hours, computer resolution, working hours .1, bonus, appraisal, transport allowance. These are the set of independent variables. Like we had independent variables from 3rd column till the 15th column. Out of the whole range, these are the only significant set of independent variables that will be used in our model for prediction. So we automatically got, by stepwise selection, the significant set of the independent variables that are going to be used for our prediction. Now let's run the summary function again on the training model to check that how much our model has improved from before. So previously your multiple R-square value was 81.53% and your adjusted R-square value was 79.79%. So see, your multiple R-square value has reduced after improvising the model, but the adjusted R-square value, which is most significant because it considers only the set of significant independent variables, that has increased from 79.79 to 80.38%. So now you can conclude that 80.38% of our dependent variable are properly explained, which is quite good. Now what we have done, we have used a package called CAR. This is a package we will need to do the multiple linear regression. So this package, before you run any package, first the thing which you need to check is that we'll go to the packages tab in the R documentation window, and from here we'll search whether CAR is present or not. You will see in most cases where you have installed R for the first time, CAR will not be present because CAR is a user inbuilt package, it is not a system inbuilt package. When you install R, by default there are certain system inbuilt packages that comes, but CAR is not part of it. CAR is a user inbuilt package. When you will not find CAR in this list, you can go to this install option. You should have proper internet connection for this. After connecting to the internet, you can type the name of the package that you need, click from the drop down and just install it. In my case it is already installed, so after installing the package you need to run this particular code to activate the package. So if the package gets activated, then automatically the checkbox beside your CAR library will be ticked. So here the CAR library, the CAR package is already activated. Now let's activate the CAR package and let's do VIF on our model. Now what is the use of VIF? VIF stands for variance inflationary factor. As I told you, one of the most important assumption of multiple linear regression is that you need to have minimum level of multicollinearity among the independent variables. That is, the independent variables should not be much correlated to each other. If the correlation is high, then the variance will get inflated and that will lead to huge amount of inconsistency. So to check for multicollinearity, we perform this function of VIF. See the VIF values. The VIF values are quite minimum. If your VIF values comes within 5 or 10, that is a benchmark generally we keep for every project, then we say that the variables have limited amount of multicollinearity or minimum level of multicollinearity using which you can work upon. So here the VIF values are quite minimum. So let's proceed to the next part. Again we have activated the library CAR and now we are going to check for autocorrelation. Autocorrelation is another important assumption for a classical linear regression model. What do you mean by autocorrelation? Autocorrelation means that when the error terms are correlated with respect to time, we call it as autocorrelation. In order to check for autocorrelation, we do Durbin-Watson test, but the assumption of our classical linear regression model is there should not be any autocorrelation in our model. So in order to check that, we do Durbin-Watson test. Let's do that test. In Durbin-Watson's test, if your DW statistic falls between 1.5 to 2.5, then we denote that there is no autocorrelation. This is one value using which you can check the autocorrelation. Another is your p-value. P-value is the probability value, that is checking the autocorrelation using the p-value approach. If your p-value is greater than your level of significance, which is by default 0.05, then you will accept the null hypothesis. Now, null hypothesis of Durbin-Watson test is that the model does not have any autocorrelation, and alternative hypothesis is there is an autocorrelation. So here you see the p-value is also 0.454. This is very much greater than the level of significance, which is 0.05. So we can conclude that there is no autocorrelation in our model. Now let's do plot.new to clear the plot window. Now in order to get this particular error of figure margins too large, you can use the PAR-MAR concept, that is PAR margins concept. So we have used this code to avoid getting the error in plot.new. Now we are going to use the training model to predict the values for training data. So we have built the model. Now we will be applying the results of training model into training data and to do prediction for the 70% of our data. We are doing the prediction and we are storing the predicted values in the train-pred object. And now let's see train-pred. So this is the predicted values of our dependent variables for the 70% of the data. These are the predicted values of your employee satisfaction for 70% of data. Now let's then check the summary of train-pred. Summary of train-pred is going to give you the 6 statistics of your train-pred object. So what do you have in 6 statistics? You have the minimum value, the first quartile, the median, the mean, the third quartile, and the maximum value. One way of viewing the predicted values is first you have called the object name train-pred, or you can do training model $fitted.values. Fitted.values also stands for predicted value, so you will get the same result. This will also give you the predicted value of our dependent variable. That is, here we have predicted for the 70% of our data. Now view train-pred I have done to view train-pred in form of a data structure. This is the value of train-pred in form of a data structure. Now I am going to apply the results of training model in a new set of data, that is for the 30% part, that is testing data. I am applying the results of training model in our testing data and predicting 30% of the data and storing that in an object called testpred. So these are testpred contains the predicted value of testing data, or testpred has 30% of the data that is predicted for our dependent variable, that is employee satisfaction. Now let's move to the next part. Now in order to check how good is our prediction, we are going to check the correlation. That is, correlation defines a degree of association between the two sets of variables. Here we are defining correlation between the predicted values of training data and the observed value of training data. So we see that the correlation is 0.9015, that is, the correlation is quite high. Then we are doing a scatter plot on correlation. So see, correlation is quite high over here. The correlation is quite high over here. And we can see the actual values and predicted values are directly proportional to each other. So because the scatter plot is upward sloping. Now we'll do the same thing for testing data. This we have tested for the training data, that is for the 70% of our data. Our prediction is quite good. Now let's check the correlation between the testing data, that is we'll be checking the correlation between the observed values of testing data and the predicted values. Here the correlation is 0.84. Previously you got the correlation near about 0.9. For testing data it is less, obviously, for the reason is that for training data we had built the model on our training data, and for prediction we had applied the results of training model on training data. So therefore you got a better correlation or high correlation. But for testing data, we have built the model or we have built the model, that is training model. We have built the linear regression model, that is the training model, and we have applied the results of the training model on testing data. That this is a new set of data. So here the correlation is 0.84, which is also very good. Now let's check the summary of it. So in summary of test spread, you got the 6 statistics of the predicted value of testing data, that is the minimum value, first quartile, median, mean, third quartile, and maximum value. And then we have done a scatter plot between the observed value and the predicted value of testing data. Okay, so previously we had done scatter plot between observed and predicted value of training data. Here we are doing a scatter plot between observed and predicted value of testing data. So we can see here that the observed and predicted values are quite associated to each other. That means your prediction is quite close to the observed values, that is your prediction is quite good. And here it is directly proportional to each other because our scatter plot is upward sloping. So this is all about our linear regression model. So we have concluded that our prediction is quite good, it is quite close to our observed value of our dependent variable, and our explained variation is around 80% as per the adjusted R-square value, which is also quite good. That is 80% of our model is correctly predicted, or 80% of our dependent variable is correctly explained. So that is also a very good score, that is our model is a very good fit. So that's all for today. So this is all about how to do linear regression or how to implement multiple linear regression using HR analytics on R.